Hello, welcome to this video. Been a while since I posted the last one. Life is, well, as full of wonderful dynamics as are quantum fields and electromagnetic waves, which moves me nicely onto today's topic. And this topic is from the question of, if we've got two visible light waves, like let's say we've got two beams of yellow light, when they combine, when they come into contact, why doesn't the energy in the visible light rays reorganize itself to produce a highly energetic electromagnetic wave such as an X-ray? Now evidently visible light doesn't do this. If it did, then visible light would be potentially very dangerous because the light waves come into contact with each other all the time. However, from the perspective of the conservation of energy, it seems plausible, and using classical definitions of momentum, it also seems like from the conservation of momentum, it should be possible for visible light rays to combine to produce X-rays and other high-energy ionising electromagnetic waves. So what's going on? Why does visible light remain visible light even if we shine the beams from two torches at each other? And this video really comes up due to kind of questions I've seen arising concerning how light waves add together. And in this video, we're going to answer our key question of, can visible light combine to form X-rays? And in particular, why can't it do that? We're going to get to an answer to this through a couple of avenues. We're going to look at the answer from the perspective of quantum mechanics, and then we're going to look at an answer more focused on special relativity. Now, it's worth saying a complete answer would be one that fully unifies special relativity and quantum mechanics and applies that understanding to light and electromagnetic phenomena. So if you want a complete understanding, quantum electrodynamics is a place to go, but you could have an entire book dedicated to quantum electrodynamics. So this is a much shorter way to get a good general picture of the answer. To begin today's adventure, it's helpful to talk about what light physically is, and then we can talk about how it can interact and what it means when two light waves add together, i.e. what type of result wave is produced and how does it differ from the original rays of visible light. So to get a clear picture of a kind of classical version of light, I'm going to show an image of a ray of light in terms of its electric and magnetic fields. This image you've probably seen before, but I'll briefly go over a few details. Might be a slight tangent, but then I'll quickly move on to Maxwell's equations, because Maxwell's equations actually are very informative in describing how light adds together, as we will see when we look at a bit of special relativity. So this is the image you've probably seen before when you were first introduced to electromagnetic waves. Now it's worth saying this is a visual depiction of mathematics, so it's something you can have in your head to build intuition, to make certain predictions, but we're not actually saying that there are literally fields which are physically moving in space, which you would be able to see if you could look closely at a light wave. These fields are mathematical things, and what we have here is just a visual depiction of mathematics. So the mathematics as a kind of reality, this visual depiction might not have. Just worth mentioning. But the key thing is the kind of mathematical properties of light that this description is showing is that light is a interaction. It's not a static thing, it's an interaction between a oscillating electric field and an oscillating magnetic field. And the two things are very closely linked. I mean, when the displacement of the electric field is zero, the displacement of the magnetic field is zero. Also on this diagram, we can see that the electric field oscillates in a plane that's perpendicular to the magnetic field. Now in this diagram, to make it look easier, the plane the electric field oscillates in is kept fixed. So we are dealing with linearly polarized light. If we were dealing with circularly polarized light, then the electric field vector could rotate, but the magnetic field vector would rotate with it, such that the planes of the oscillation of the magnetic field and the oscillation of the electric field are perpendicular to each other at all times. And also the relative amplitudes between the electric and magnetic field are also related, it turns out. So there's a lot of interrelations between electric and magnetic fields. Some are useful in gauge theory, which is helpful when doing calculations in quantum electrodynamics, but for our purpose, this interconnection implies that the mathematics that this is representing should have equations which link electric and magnetic fields, and that's exactly what Maxwell's equations do. So Maxwell's equations describe electromagnetic fields generally, of which a electromagnetic wave, so what we might call light, is an example. And X-rays would also be an example of an electromagnetic wave, just one oscillating at a higher frequency. So this is the first of Maxwell's equations. It's a source term for the electric field. There's also a source term for the magnetic field. That's set equal to zero because in nature we don't find any north poles by themselves or south poles by themselves. If we have a magnetic field, we always seemingly have a north and a south pole, and therefore the flux of the magnetic field in a kind of a closed surface is zero, and that's essentially what our second equation is saying, but in differential form. And then we get on to the equations that relate the electric and magnetic field. So the first of these two equations that relate these fields discuss how the curl of the electric field is related to the rate of change of the magnetic field, and the last one is kind of that one in reverse. But the last one has a kind of like extra term, the term with our kind of current vector J, and that extra, well, I suppose it depends what experiment you're doing the extra term is. In some contexts, the extra term might be the current vector J, but the extra term that Maxwell found, and I apologise, I just had a minor camera incident, so I'll just hold it here. But the extra term that Maxwell found said that there is a relationship between how the magnetic field changes in space and how the electric field changes in time. Now, this is the mathematical modelling of light And this is what we will focus on using, because the mathematical model describes what exists, although it's helpful to have the visual description in mind. So now, given Maxwell's equations, can we get to an answer? Does Maxwell's equations provide an answer for why visible light doesn't combine together to produce X-rays? So hopefully this will transition nice and smoothly. If there is a sudden change to what's happening, I've just been outside, and now I'm back inside, but by the magic of YouTube, a kind of a YouTube version of relativity, although a couple of hours have passed for me, probably only about 2 seconds has passed in the final recording of this video for YouTube. For the YouTube perspective, a couple of seconds ago, we were talking about the beams of torchlight meeting and what would happen, so how the energy would be conserved. So there's a couple of really ways that this could happen, which is consistent with the idea of the conservation of energy. So firstly, the waves could meet, and then they could create a resultant wave that is genuinely new. And this new wave would be new because it would have a different frequency. It would have a higher frequency compared to the incident beams of yellow light from the torch. And this wave has higher energy because it's energy combining from the two initial waves, and it kind of feels like, okay, if a wave has more energy, maybe it will just oscillate more quickly. That kind of makes intuitive sense. And we have a water wave, and we cause it to oscillate more quickly, we'll probably have to have supplied more energy. So from the conservation of energy, it seems that we can create a resultant wave with a differing frequency. And in that context, the resultant wave is genuinely a new wave, and the two original waves have kind of like combined and are no longer present as the two individual waves. And to show what that would look like, it would be like if we were going from the top image with our two initial waves to image number 1. And that seems plausible in terms of the conservation of energy. And if that could happen, then then visible light could combine to produce X-rays, which evidently doesn't happen, but it seems viable. What actually happens if you've got two visible light waves meeting is that you create a resultant wave, but that resultant wave is just thinking about the net effect of the two individual waves. So the two individual waves remain, but we can think of them as forming in our minds a resultant wave. But because the two individual waves still exist, this resultant wave has the same frequency as the individual wave, but the amplitude of the resultant wave is bigger. And again, if you have a bigger wave, it feels like, okay, that wave has more energy. I mean, a tsunami has a lot more energy than a wave of similar frequency, but a wave which is just a small ripple in a pond. Tsunamis are dangerous. Ripples on ponds, at least for human beings, are not nearly as dangerous, thankfully, because I love swimming. But anyway, what light does when it meets is something like number 2. Now in number 2, I suppose when they meet, they constructively interfere, but that's just a kind of technical detail I could leave aside for this video. Essentially, in number 2, the amplitudes of the individual waves can be thought of as adding together, really what's happening is our two individual waves still exist, but they're superimposed on top of each other, so we can think about them together as just one larger resultant wave. So in reality, number 2 always happens and number 1 never happens. So why is that? And to answer that question, we're going to need to bring in quantum mechanics, special relativity, and help get there, we're going to introduce a initially fairly classical notion of the electromagnetic field via a rather cool thing called the Maxwell field strength tensor. It sounds cool, and it is really cool, I think, personally. So we've mentioned that Maxwell's equations are key to how we think about light. And in order to explain why light adds together by changing its amplitude rather than its frequency, it's helpful to write Maxwell's equations in terms of something called the Maxwell field strength tensor. Now, you could argue as soon as we do that, we are using special relativity, which we are, but it would be strange to introduce the tensor without relativity, but you could get to the tensor without knowing relativity if you knew Maxwell's equations. So I'm going to treat the Maxwell tensor as classical, even though the reason it was developed was to think of it in a clearly relativistic context. Well, to think about light in a clearly relativistic context. But to just summarize, Maxwell's equations, well, the ones at least involving the curl of the electric and magnetic fields, hint at a deep connection between these two fields. And because the curl in one field implies that another field changes in time, and a wave is about symmetry between how a wave changes in space and how it changes in time, it seems like the electric and magnetic fields not only are dependent upon one another, but actually they're part of some unified structure. And that structure we call the electromagnetic field, and the strength of the electromagnetic field is given by the Rankine tensor known as the Maxwell field strength tensor. I will just sometimes call it the field strength tensor for the purpose of this video, because we're not talking about really any other type of fields, save at the very, very end. So here is a definition for the Maxwell field strength tensor in terms of the full potential of the electromagnetic field. And the full potential is a 4 vector because this electromagnetic field exists in space-time. Now, if all of that sounds like a lot of jargon, I would recommend either checking out my video on tensors, or even more helpfully, most likely, checking out my video on 4 vectors in the special relativity playlist. And that's just if you're feeling confused over kind of like the notation used here, or what 4 vectors are, or why we're using 4 vectors. But anyway, this is our field strength tensor. And the reason why light adds together to create a wave of a larger amplitude rather than a differing frequency is because of this field strength tensor and various aspects of it. So we're going to start with explaining why visible light can't combine together to produce X-rays by considering a quantum mechanical way of thinking about this situation. And it's fairly customary in physics to denote quantum mechanics using the letters QM, so that's what I'm doing here, to distinguish it from a special relativistic way of looking at this field strength tensor. So in quantum mechanics, we learn lots of new things about particles, and also about what are classically considered waves, such as light. So in classical physics, light is an electromagnetic wave described by the field strength tensor, and the wave is continuous, and the field strength tensor is also continuous. But when we bring quantum mechanics ends up informing us that actually this field strength tensor isn't continuous, and that's by virtue of quantizing our four potential, which is used to define the field strength tensor. And traditionally in quantum mechanics, we put a hat above something if it's quantized, because when something is quantized, it becomes an operator. And we denote operators by putting hats above them. Hats can also mean other things in mathematics, but for the case of quantum mechanics, a hat usually means we're talking about an operator. Unless there are so many operators that we just don't bother with the hats, which does sometimes happen. But for this video, I'm keeping the hats to denote an operator. And as I said, the electromagnetic field tensor is quantized through the quantization of our four potential, so we put our hats above our components of our four potential, so A nu and A mu. And what this kind of a physical picture of this quantization is that it turns this continuous electromagnetic field into like chunks. And we can think of these chunks as particles. And we call particles of light photons. And essentially what the operator version of the field strength tensor does is create or annihilate photons. It's analogous to raising and lowering operators in standard quantum mechanics. So when we say we have a kind of like electromagnetic field, we're talking really about the average, a kind of like statistical average of this kind of quantized field strength tensor. And so we're saying something about how many photons we have present. And when light meets, we're therefore getting kind of like lots of photons meeting up, so they're kind of like in the same region of space. But just because the photons are close together doesn't mean we have somehow changed the photons. And so because we're not changing the photons, we aren't changing really the details of how the electromagnetic field is quantized, and therefore we're not changing the frequency of the classical electromagnetic wave, which is a kind of statistical average of this quantum electromagnetic field. So it's because when light meets each other, all that is happening is photons are getting close together. or closer together than they were previously, because we're the light waves are meeting and overlapping in some region of space, but we're not actually changing the photons themselves, and so we're not going to be creating a wave with a different frequency than the waves we began with. So that's one way of explaining why visible light can't combine to produce X-rays. It's because visible light photons will always be visible light photons. Now, there are caveats to that statement. I'm trying to answer the question very generally, so if you know of exceptions to what I'm saying or ways in which it is in some technical ways wrong, I do apologise. But for the sake of this video and giving a general explanation, I think this is a fairly decent one. So when light waves meet, the photons themselves don't change. We just have more photons, so we have a wave with a larger amplitude. So that's kind of the quantum reasoning. Now we're going to move on to reasoning with the help of special relativity before quickly concluding everything we have said. So now we're moving on to our last point as to why visible light can't combine to produce X-rays. And we're going to use, you probably guessed it, but we're going to use the field strength tensor yet again. So I won't go over it again, but here were the details of how the field strength tensor is classically defined. Now, I mentioned earlier that part of the motivation for defining the field strength tensor is special relativity. So although we're calling this classical, there are details of special relativity hidden within this. One thing is that this equation is a Lorentz invariant. So if we apply a Lorentz transform, then the form of our equation isn't going to change. But we can be a little bit more specific than that. So the field strength tensor is a tensor, and it's a tensor in the context of special relativity, so transformations, Lorentz transformations and Poincare transformations more generally. And we're using space-time algebra to represent it. But this means that this equation is very trustworthy, even in a special relativistic context. And we can use the equation that defines the field strength tensor to rewrite Maxwell's equations. And now special relativity comes from Maxwell's equations, so providing we wrote the field strength tensor in a Lorentz invariant form, which we have, then we're not going to be doing anything wrong. We're not going to be breaking the physics by rewriting Maxwell's equations in terms of this field strength tensor. Essentially, Maxwell's equations and the field strength tensor are compatible because they're both built on the principles of special relativity. And when we use the field strength tensor, we reduce Maxwell's equations down to just two. So we go from 4 classical equations to 2 relativistic ones. And these are our pair of relativistic equations. Now, the first one is a source term. Now, for the purpose of our thought experiment, we have visible light moving through a vacuum and then just kind of like passing through each other. So we're thinking of light moving in a region where there isn't anything to generate a electromagnetic field. And that means that the first equation becomes equal to 0. So the top equation is equal to 0 in our thought experiment. It isn't always equal to 0 in a more general setting, but in our thought experiment, we can set the derivative of the field strength tensor to 0. Because there are no source terms. Light is moving through a vacuum. Now the bottom equation, that is always 0. Doesn't matter what's happening, that is always 0 in any thought experiment that is compatible with Maxwell's equations. And the bottom equation uses an interesting bit of notation, those brackets around our indices telling us that we are anti-symmetrizing our tensor. It's a kind of notation that allows us to write the equation in a much more condensed and neat form than if we didn't use the anti-symmetrization procedure. But I think on one of my videos I wrote the bottom equation out more explicitly in terms of derivatives of the field strength tensor, so you can do that if you like. But anyway, these two equations are equivalent to Maxwell's equations. And a really cool thing about them is they are linear. And because they are linear, it tells us that if two light waves meet, then these light waves will not interact in the sense of the photons won't start gluing together. We'll just end up with a resultant wave, which we can think of as the sum of the individual waves. So the resultant wave is just us adding together the two individual waves. It's the result of both of them, but both the individual waves still exist. The two individual waves are still both existing, and so in that sense the two waves haven't combined together. Most certainly the photons can't combine together to produce a photon of higher energy, so visible light cannot combine together to produce X-rays. But this kind of linearity in Maxwell's equations, and what we said earlier about photons not interacting, are very, very linked together, and I'll talk just a lot about that in the conclusion before we just say, well, before I say Merry Christmas, essentially, although I do hope to release another video before Christmas, but we will see. So we have now reached the conclusion of this video, and so essentially combining everything we've said, the insight from kind of special relativity and quantum mechanics, we can say that photons don't interact with each other, and the reason for this is that they are described by fields which are linear. They are linear differential equations. At least if we're using the Maxwell field strength tensor. Now you might wonder, is there something like light, so a massless particle, which isn't described by linear equations? And it turns out there is. There's the gluon. Now the gluon is similar to light, but whereas light is a quantization of the electromagnetic field, a gluon is the quantization of the field referring to the strong nuclear force. So the gluon plays a vital role in the formation of protons and neutrons. It also plays a vital role in holding the protons and neutrons together within the nucleus, and the strength of the strong force explains why nuclear radiation emits alpha particles in the form of helium nuclei, and the gluons explain a great many things. Gluons, and thinking in detail about gluons, also gave birth to string theory. So gluons are quite fascinating. But because gluons are described by nonlinear equations, they can interact with each other. So we consider gluons as having some strong force version of charge that would allow gluons to interact with each other. Now, as we said, photons can't interact with each other. Now, photons can interact with charged particles, as it's described in quantum electrodynamics. And photons' interactions with charged particles is what allows us to see objects made of atoms, and therefore made of ultimately charged subatomic particles. So the fact that light interacts with charged particles is very important. Otherwise, objects would not be emitting or interacting with light. But because light interacts with charged particles, but light doesn't interact with itself, we say that light is uncharged, and therefore the photon is electrically neutral. So the idea that the photon is electrically neutral, the idea that the photon is described by a linear set of equations, these things are very linked together. And if you would like to learn more about the links between interactions and the linearity in differential equations, I would recommend looking at chaos theory if you want to think about it very generally in the context of classical physics, or taking a little look at quantum field theory, which will be particularly helpful for a deeper dive into topics covered in this video. But I really want to keep this video below 40 minutes, so I'll just wish you a really good Advent. Hope you have an incredible time, lots of lovely mince pies too, and hopefully make a video before Christmas, but if not, wishing you a fantastic Christmas ahead, and looking forward to sharing more wonderful physics in the new year. But for now, keep exploring and keep being adventurers of our incredible universe.